Perfect. So yes, hello everyone. Thank you for making it until the end. And thanks a lot also for the organizing committee. It's really a pleasure to be part of this conference. So what I will be presenting today is joint work with Harry Miller from the University of Manchester. And it's about the second law of thermodynamics, in particular in a setup where you consider a small system that you are driving in time while exchanging heat with a bath. Okay, so you extract some work or you spend some work to change the Hamiltonian of the system from an initial point to a final one. And the second law of thermodynamics tells us that the cost of this transformation is lower bounded by the change of free energy, or equivalently that the extracted work is upper bounded by minus delta F. So this is a sign convention that I will be using in this talk in case, okay, some relations look a bit strange. So indeed, and then we know a lot of things about this relation. So we know how to saturate it, and this is by doing an infinitesimally slow process. But also right now, also with the development of stochastic thermodynamics, we understand very well also what happens in finite time. Okay, so we can relate this extra work, this dissipated work, to entropy production, and we have ways to minimize the entropy production, and also we understand how we scale until the reversible bound, let's say. And now in this talk, I want to take as a starting point a different inequality, which is also very well known here, which is by Jarzynski, and it's a consequence of the fluctuation theorem that makes a probabilistic statement about this process. So in particular, what this tells us is that the probability to violate the second law is upper bounded by an exponential function relating also delta F and the amount by which we want to violate it. And what I will try to do in this talk is to make a similar analysis that has been done for average work, but for this probabilistic, this probability of success. Okay, so I will discuss how it converges to this bound and also how it relates to entropy production. So this is the setup. So as I was saying, what this inequality tells us is that if we want to extract work beyond the change of free energy, say to beyond some parameter lambda, now this is exponentially suppressed. Of course, for macroscopic systems, this is negligible, but this is not the case for mesoscopic or quantum systems. So it's interesting to see what are the limits, and in particular, how to saturate this bound. So this question was investigating in this very nice paper by Cabina, Mari, and Giovannetti a few years ago. And the first thing that they did is to actually find a refinement of this law, because it's clear that if you want to maximize the probability here, you will have some penalty, okay, because the average must lie below this point, so you must have some penalty, okay, and you can ask that you don't want this penalty to be smaller than a given value, okay, so you can say, okay, that's the most that I can take. And then you find this refined version. Okay, so when you take this penalty to minus infinity, then you find again Jarzynski's bound. And it's worth going through the proof of this result because it's very simple. So you start from the fluctuation theorem, and then you split it into two parts. And then you take kind of a best case scenario where this exponential is the smallest possible value, and then you immediately get this bound. Now, it's important to notice that to saturate this inequality, you need this kind of distribution. So you need a two-peak distribution where the probability of you only extract work either when you are at this desired parameter lambda or when you are at the penalty, okay? Because otherwise, if you have any other probability, then this would be a strictly lower bound. Okay, then the next question is how to saturate this bound. And this was also addressed in this paper. And the idea is to combine two isothermal processes with a quench. And it's enough to take a two-level system. I mean, you can take a system with more energy levels, but a two-level system is enough. And the intuition is the following. So if you have an isothermal process, then we know, and I will also discuss later, that there are no work fluctuations. So in a perfect isotherm, you have actually deterministic work extraction. Now, if you combine this with a quench, that this will lead to this form of the distribution, yes, you end up with what you wanted. And of course, by choosing properly this EA and EB, then you can make it so that the two peaks of this distribution are where you want, basically. And you can argue also that this protocol is unique, at least for a qubit system, and if you have some Markovian dynamics, and otherwise that this structure is also preserved for more general systems. Okay. Now, of course, the limitation, as with the standard second law, is that to do a perfect isotherm, you would need infinite time. So, of course, this in practice is not possible. And this is very well observed in this nice experiment that they did in the group of Jukka Pekula a few years ago. So you can basically, this is a basically driven single electron device, and you can see that this kind of structure where there are two slow isotherms separated by a quench, and the work distribution, it has the desired form. So you have a peak that is a penalty and a peak that is a desired work extraction. But of course, you don't have perfect delta distributions, but instead you have distributions with finite width. And this is because you are doing this experiment in finite time. Okay, so this was in a way the starting point of our work, where we wanted to investigate optimal protocols for this probabilistic task. Okay, so let me explain a bit the framework. So I will reconsider the quantum system, but actually in this part of the talk, everything is classical, because I will only consider that the energy can be driven in time. Okay, and then I will consider at each instant of time the thermal state as a fixed point. Okay, so it's actually just the rate equations. So just a classical, essentially classical system. And there is a subset, given this general framework, of processes where basically you discretize this evolution and you consider that you either do a quench where you drive the system, or you let it relax with the bath. Okay, so these step processes, they are useful because you can get more analytical insights, but then we can always go back. I will explain this later, okay? But let's keep in mind also these discrete processes. The second important point of this talk is that I will be considering slow driving. So basically linear response expansion over h dot. In this case, it's well known that you can divide the work with a reversible term plus a quadratic form. Okay, and in general, you can write this quadratic form as a function of the Lindblad master equation that you have. And this we've been studying in recent works. But in this case of discrete processes, where basically you expand over n, the number of steps, then this quadratic form sorry, is just a susceptibility. Okay, so it has a very nice interpretation, and this goes back to the 80s. Okay, and in this case, also you have a very nice, well, in general, when you have this quadratic form, you have a very nice way of minimizing and optimizing these processes in the framework of thermodynamic geometry. And this goes back to seminal works in the 80s, and also Crookes and Sivak. They also extended this to the stochastic thermodynamics, and more recently we've been looking at the quantum regime. So let me say a few words about this. Indeed, so the idea is that because you can express the dissipation as a quadratic form, and this matrix actually is positive definite because of the second law, this defines a metric in the parameter space of thermodynamic protocols. And then, given that you have a metric, you can also define a length. And then using Cauchy's bars, you have this famous inequality that relates the dissipation to the length squared of the thermodynamic path. Okay, and if you then divide this with the entropy production, And you have this nice relation between entropy production and the length of the path. So the first consequence of this is that if you want to saturate this bound, then you need this integrand to be constant in time. Okay. Now, what this means is that if you fix the path that you go from the initial Hamiltonian to the final one, then optimal drivings, they have constant entropy production rate. Okay. The second consequence, which is also very natural, is that the optimal protocols, they are those that correspond to geodesics in the thermodynamic space. Okay, so they are those with the shortest length. And in the case of this standard thermodynamic metric, we also have an analytic expression for the length, which is of course very useful. So yes, then going beyond the first moment, it's also known that actually the word distribution for these slow processes, it takes a very simple form, because it takes a Gaussian shape with the first and second moment related by the fluctuation dissipation relation. So we really have a very good description of slow process, okay, because we understand very well the average dissipation and how to minimize it. And from this, we can actually build the full distribution. And this also describes very well, of course, experiments. So yeah, this is the summary. And with this, we have all the tools needed. Because now I go back to the optimal protocol that I was discussing, that remember it was consisting by two perfect isotherms separated by a quench. So now what we can naturally do is change these isotherms at some finite time but slow process. And as a consequence, these Dirac deltas, they will become Gaussian distributions. Okay, so the word distribution will look like something like this. And it's very easy to see that the probability of success, it's basically related to an error function, okay? Now, in this error function, you have some parameters that depend on the boundary points that you choose. So initial and final energy, but also this quench in between. But now we also have a term that depends on the process, okay, which is entropy production that is happening in these parts of the process. Okay. Now, kind of the crucial realization is that this probability of success increases monotonically when decreasing the entropy production. Okay, so this means that, of course, we can use all the tools that we know to minimize average entropy production to also maximize this term. In particular, as I mentioned, this entropy production is directly related to the length, the thermodynamic length between these parts of the protocol, which has a nice expression, at least for this discrete process. Otherwise, the length is not known, but at least you still have this geometric, let's say, interpretation. So let me show an example of this. So here we have Jarzynski's bound. So we see that we only converge to this bound in infinite time, or when the number of steps goes to infinity. And here I'm comparing a geodesic protocol with a linear one. Okay, like what they did in the experiment, essentially what they changed the energy levels linearly in time. And you can see that indeed for finite time, we see important advantages with respect to the linear protocol. So this is nice, but this still depends on these 2 points. So if we really want to get a general result, then we need to maximize this success probability, this term, over all possible EA and EB. And then the result of this maximization, it will only depend on the endpoints, in the same way that the second law of thermodynamics only depends on the endpoints. So we can argue that we have a finite time correction to this law. So this maximization in general can only be done numerically, or at least as far as we know. And then you get, it's still quite easy because it's just two parameters. And we get the plot like this. Okay, so here you can see the best possible protocol. And for example, we compare it to the best linear protocol, and you can see how you approach Jarzynski's bound. And even if in general this is numerical, we can get some analytical insights. So what we can argue is that how you converge to Jarzynski's bound, this goes no faster than the total time of the process, or if you want the number of steps here, the square root of time, okay? So this convergence goes like 1 over square root of time at most, okay? So for example, for this particular protocol, this exponent here is 0.44. Okay, so this, at least to us, was a bit surprising, the fact that, because usually for the second law, you converge as 1 over tau, but in this probabilistic task, you converge as 1 over square root of tau, or that's the best that you can hope for, okay? And of course, all these terms depend on the length and these things that I described. So with this, I move to actually, so I wanted also to say a few words about quantum slow process, because as you noted, everything that I was saying here holds for classical process in a way, so in the sense that there is no quantum coherence. So I wanted to now also say a few words about some work that we did together also with Matteo Scandi and Janet Anders about what happens when we have quantum coherence. Okay, so remember that I said that if we have a classical slow process, the work probability distribution will become a Gaussian distribution with the first and second moment related by the fluctuation dissipation relation, which is of course very nice and very powerful. But what we realize is that when you go to quantum slow processes, this relation breaks down, okay? And basically what you can see is that the work fluctuations in the linear response regime, they are a sum of 2 contributions. So you have a thermal contribution that comes from the thermal fluctuations, and a quantum contribution, okay, that comes purely from quantum coherence. So let me show this by a simple example. So for example, imagine that we have a quantum harmonic oscillator that we are driving its frequency. So of course, when we drive the frequency, we are continuously generating quantum coherence because the driving doesn't commute with the full Hamiltonian. Now, this is also in contact with a thermal bath, which is also trying to decohere this system, and so we have an interesting interplay. Now, if you look at the work fluctuations, okay, so you can do it by unraveling the master equation, for example, but if you look at the work fluctuations, basically you see something like this. So here I'm plotting basically this term, the fluctuations and the dissipation. And you clearly see that when you go to the high temperature regime, you have the standard fluctuation dissipation relation. But when you go to very low temperatures, then the quantum fluctuations start dominating. Okay, so we clearly see how this well-known classical relation breaks down. And this has some interesting consequence, in particular that the work distribution becomes non-Gaussian. So even if you go slow for quantum process, you always stay non-Gaussian. And another consequence, and this is what I wanted to discuss here, is that now minimizing entropy production is no longer equivalent to minimizing work fluctuations. So before, by minimizing dissipation, we could use the same tools, the same metric, and all this geometric approach to also minimize the fluctuations. But this is no longer true here. Okay, but what we showed is that you can also build a thermodynamic metric for the quantum work fluctuations. So basically, for example, you can express some figure of merit that is a combination between dissipation and fluctuations, and we can build a thermodynamic metric for every value of alpha. And through this thermodynamic metric, for example, then what we can do is optimize. So basically, either minimize dissipation or minimize fluctuations in this toy model of a quantum harmonic oscillator in contact with a thermal bath. And these are some results. So if the classical relation would be true, basically by minimizing dissipation, you would also be minimizing fluctuations. But here instead, you see there's kind of a Pareto front. So there's a trade-off. So you either minimize fluctuation or you minimize dissipation, but not both. And with this, I go to the conclusions. So basically, I explain a framework to optimize finite-time probabilistic work extraction. Then I argued that the maximal well, so I showed that the success probability, the maximum success probability, can be expressed in terms of thermodynamic length. And we also get some insights of how you converge to Jarzynski's bound. And then in a second part of the talk, I discussed the breakdown of the work fluctuation dissipation relation in quantum systems. But I also argued that you can construct a geometric framework for minimizing both work fluctuations and dissipation. So let me finish also by giving a few references. So the work that I explained is this probabilistic work extraction. We put it recently on arXiv. But this is part, say, of a series of works about geometric quantum thermodynamics. So in particular, this one here, it's a review. So if you're interested, I think it's a nice way to get into the topic. And in the last part of the talk, I talk about the quantum work distribution. And this is based on the following papers. Thank you very much.